Good afternoon, good evening, or good morning to the NXP Campus Connect session today. Today I'll be going over speaking about UWB. It's a new technology. I'll be talking about UWB hardware, the IP, then the infrastructure, and then how do we combine the hardware and software to enable it on the UWB platform. So throughout this presentation, when I use some of these terms, when I say UWB, it stands for ultra wideband technology. When I say kind of hardware, it means hardware, FPGA, silicon, SoC, chip, the physical hardware, right? And for software, throughout this presentation, it means software, bootware, firmware, middleware, all the way to the application layer. So it's a generic term, software I've used through these presentations. Okay, let's go to the next foil. Speaker bio. Hey Manish, thanks for introducing me. So I'll kind of move to the next foil. Just a quick one. I work at NXP Bangalore. I'm the verification lead for UWB, NFC, and WCS chips. Thank you. Let's go to the agenda. So I've kind of, as Manish called out, I've tried to cover a bit high level, and then I go deeper into the UWB as well. So I'll begin with, on the agenda, I'll begin with NXP corporate overview, what markets we operate in. Then, since the target audience is university audience or engineering students, to some extent practicing engineers in the hardware or software industry as well. So let's refresh some of the math and physics concepts which are relevant to UWB. Then I'll kind of present over UWB user, how is getting the advantage, benefit of using a UWB enabled device. And then I'll define the UWB as a technology. Then delve into the SoC, the hardware portion, the hardware software platform flow methodology. Then go deeper into ultra wideband technology, the ranging techniques which are used in UWB. Then the UWB packet or the frame structure, then the UWB hardware software co-verification for quality. Right, and then the last few foils, the UWB, how it intersects in our smart world today. And then for the university audience, the UWB careers and the conclusion. The last 15 minutes, I'll keep them open for Q&A. So while I walk through the presentation, please make a note of the foil number on the bottom right. So when you ask a question, if you could refer the foil, then it'll help me get into the context and have a good interactive discussion. Okay, let's go to the next foil. So this is the NXP corporate charter. We secure connections for a smarter world, and the target markets NXP operates in. The first vertical is automotive. The second vertical is industrial and IoT. NXP has solutions in this vertical market segment. And the third is the mobile market segment. Also, we call it as a connectivity or security market segment. And UWB falls in this market vertical. So today's presentation would be on this space. Likewise, the fourth one, vertical, is a common infrastructure. This enhances the infrastructure or deploys infrastructure for the next generation communication. Okay, let's move now. So I kind of titled this as a pop quiz. Well, it's not an examination here, but nevertheless, let's refresh our math and physics principles, these are relevant to UWB technology, right? So begin with starting with the very basics of math. All of us, we do the math operations, right? Addition, subtraction, division, multiplication. Given two values, we know whether it's equal to, greater than, or less than. Right, and a little bit of geometry between two shortest points, the path connecting these two shortest points, that's a straight line. We measure the straight line in centimeters or meters, that's a unit of measurement. And a little bit of trigonometry, where we have a right angle triangle here as shown on the screen, given we know the value of theta, and the right angle triangle is 90 degrees, then we can perform sine functions or cosine functions to calculate the length of opposite or the hypotenuse, right? These are basic math, right? Then a circle, given a circle, given a circle, we know the value of pi. So the circumference of the circle is 2 pi r, and the circle has 360 degrees around it from the center. And if we were to kind of calculate, take a sector of the circle, and given the radius and the degrees, then we can calculate the theta or the angle of this sector, right? Likewise, moving to a bit of physics, speed, distance, time. We know the relationship between speed, distance, and time. If given the distance and time, which are variables, right? How far you have traveled, or how far is the object, or how much time, how many seconds does it take to go through the distance, right? So that's distance is in meters, time is in seconds. These are reference variables. And speed of light, as represented by the mathematical symbol c, which is also the radio frequency signal, right? The radio frequency signal they propagate at the speed of light, that's meters per second, and it's a constant, right? Then a little bit of more physics and optics, wave propagation. So we have an incident signal which hits a surface. For example, a mirror, much of the signal gets reflected back, some of the signal gets refracted and goes through, right? That's the basics of physics and optics. And then a little bit of advanced math, Fourier transforms. We apply the Fourier function for frequency domain to time domain transfers. Likewise, for engineering students who have taken communication as their core subjects, so sampling theorem or the Nyquist frequency, what it states is if you have a continuous waveform and you need to sample the continuous waveform at twice the frequency to be able to faithfully recover the signal or reproduce the signal. So these are the basics. So as we go through the UWB technology and the methods for ranging, right? So keep in mind to recollect these basic math and physics principles in each of the foils, then you'll be able to grasp the concepts. Okay, let me move to the next foil. Here, what we have is a user, I just called him Theo. User is in the middle of his house, and if you follow the blue dotted lines and pay attention, read the blue labels in this, right? So user Theo is carrying a UWB enabled wireless device in his hand, in his palm. And with respect to the user's location, the light point or the light switch, that's 3.2 meters away at an angle of 30 degrees. And on the ground floor, the garage or the car in the garage, that's 4.9 meters away, and it's at a 60-degree angle with respect to the user Theo location. Likewise, the main door access, user Theo can lock or unlock the main door. So that's 5.8 meters, 172 degrees with respect to the user Theo, right? So these are the different lifestyle points inside a house. And how, now let's kind of, as we go through the next points, how UWB technology enables user Theo to operate each of these lifestyle points using a gadget, right? Okay, let me go to the next foil. So definition of UWB. So UWB technology, it enables secure ranging. When we say ranging in terms of math or physics, it's a distance, time taken with respect to the gadget position, right? So UWB technology, it enables secure ranging, very precision sensing in terms of distance and angle, and it creates a new dimension of the spatial context for wireless devices. It's like a three-dimensional information, right? So the three-dimensional context or the three-dimensional information that's analyzed, that's provided to the user with the UWB technology. This enables decision making, also enables device management, right? And as an engineering standard, UWB, that's standardized as part of IEEE 802.15.4Z, right? This is the standard which defines how UWB technology operates. Right? So what I have here is a video of a car with UWB technology enabled inside. So let's take a look how this is an existing technology. So let's take a look how the user or the car owner benefits from UWB technology. Let me play the video. Okay, um, so in the video, what we have seen is we have a father and son. The father carries a UWB car lock unlock form, and UWB senses the pattern, the personal signature of the father, and gives access to the car. But when the son tries to mimic or imitate and tries to unlock, it denies access, right? Also, UWB is deployed for the safety sensors, and it kind of cautions or alerts that, hey, the child seat is not locked properly, right? So this is where UWB in a car senses the ranging of the distance, and also very precision down to the centimeters kind of enables for us to have a secure car access, also a safe travel, right? Let's go to the next file. So now switching gears on the SoC infrastructure, right? So we have a technology. Now, what's the methodology? What is the flow we need to follow, right? We need to kind of develop through this flow to enable this technology in hardware, and also develop the software. And then how do we integrate it into the platform, right? So let's focus first on the hardware infrastructure. This is partitioned into front-end flow, which is what I'm sharing on the file. So the flow diagram is like UWB technology. We have a discussion with the customer. We collect the customer requirements, and then we map the customer requirements into a SoC high-level architecture. And then the SoC high-level architecture, we break it down into specification of blocks, specification of few blocks put together as a subsystem, then specification of how this subsystem and blocks interface with the other modules or the other systems, right? That's all in the hardware, right? And once we have the specification internally reviewed, ratified, then we move to RTL logic design. This is Verilog, system Verilog based languages. And this RTL logic design from the designers, then it gets passed on for functional verification and validation or emulation, right? So what do we do as part of functional verification, right? So we know there are IPs or designs, right? They have the features which have been integrated. And any SoC would have the global features like power, clocks, resets, right? And then we kind of build this design, and then we simulate this design, right? To verify the intent, to validate the intent, right? Intent, when I say intent, it's specification versus, hey, what is the expected specification as an expected versus what's the actual design response, right? So that forms part of the functional verification validation on the left side with respect to the IP design, power clocks and reset. Now, once we know the functionality at the hardware level is verified, validated, then what we do is we bring in the software boot code, we bring in the software firmware, and we kind of stress this design through all the interrupts, whether all the interrupt lines are toggling, wiggling, what are the interrupt service routines, and then we perform DMA, direct memory access between source and destination. This could be memories, or this could be between memories and IOs, input outputs to the hardware, right? And then we do performance verification, performance validation with this hardware design combined with software as part of the front end flow, right? So this process goes through, and we kind of move to the next step, where the goal is to have a bug-free design spec versus the design implementation that's been verified, validated, and then we proceed through the regressions. Once the regressions are 100%, right, then we know, hey, the intent is met, this design is good to go, right? So there are few other loops which are not shown here in the flow diagram. So when we find a bug, we go back, look at the RTL design implementation, whether the design implementation is correct, or is there a deviation from the specification. So then we know his specification is correct, then it's not a design bug, it gets fixed, then we repeat the entire functional verification, validation, emulation cycles until we get to a bug-free design. Okay, so typical development cycles are based on the SoC, complexity of the SoC. This could be a few months to many years based on the industry. So now we have a design, it's bug-free, it's 100% regression pass rate. So what do we do next? The next step is, let me move to the hardware infrastructure file. This is backend flow, right? So we take the design, we use synthesis tools, we perform logic synthesis of the design, right? So at this point of time, then we read in the libraries or the standard libraries, which are the AND gates, OR gates, NOR gates, the basic gates, as well as the flip-flops, right? As well as the register libraries. And then we also read in what are the memories which are instantiated in the hardware, right? And then what are the interfaces or the IOs or the IO pads. So with these library components on the left and right, we perform the logic synthesis. So at this point of time, what we have is a netlist, or a functional description in form of a netlist abstraction, right? The functionality is good. However, we would also want to mass produce or take this hardware to production, right? So how do we catch defects as part of the SoC fabrication process? So that's where the next block, which I'm showing here, DFT, design for testability, this comes in, where we take the functional design, the netlist level abstraction, and introduce test hooks or testability observation points. We call them scan flops or ATPG. And then at this point of time, from DFT, output of DFT, so we have a functional netlist along with testability, and then we press this design through a static timing tool or a static timing analysis. For example, if the clock is, let's say 100 megahertz, right? So then we kind of close the timing for this design for 100 megahertz plus a guard band on top of it. So once we have the timing close design, then we do what is called as P&R or place and route, where on the die, the entire design is placed based on the IOs, based on the interfaces, based on the clock frequencies, right? And then after we do place and route, if there are any, again, engineering fundamentals, any circuit will have a setup and a hold time. So once we do the place and route, we again review the setup is met, hold times are met, or holds are fixed. And then we have the final post layout net list with power, with clocks, with the reset propagation, and with the functionality. So at this point, we perform GLS, stands for gate level netlist simulations, with the standard delay files which are generated as part of the STA process. So then once we know the GLS is a structural design, right? Once the GLS simulations are regressed, they pass 100%, then we release what we call the design at this point, at this block level, right? At this tapeout, right? At the tapeout level, it's called a GDS2. So the GDS2 is FTP'd to the fab. Then we do the tapeout. And the next step from the fab, we would get the silicon or the wafers, right? So we take the wafers, we cut them, we identify the good wafers thanks to the testability hooks we have put in. And all the good wafers are, the good parts are cut from the wafer, they package into package parts, and the silicon arrives in the lab. So this is the backend flow, right? So let's continue. So now we have hardware, we have package parts in your hand. Let's see now what do we do next, right? So then we move, then we need to kind of focus on here. I have the hardware, I have the software. Now, how do I enable this on the platform? When I say platform, it's a motherboard, a simple definition, right? So we plug in or solder, if you will, basic terminology, silicon onto the platform, right? And then this combined hardware and software, it's powered on, it's booted up. If there is any issues, we debug them. Then we press through, we invoke all the software routines, all the firmware routines, which exercises the different functionality of the chip, SoC. Then we get back to our UWB protocol checks. We perform the protocol checks that the hardware plus software combined together has passed the protocol checks. And then ranging is the UWB use case, right? When you say ranging, from a wireless enabled device, what is the distance, what is the angle, right? So then we do the UWB ranging demonstration. And then we press through the UWB compliance checks as outlined in the IEEE 802.15.4c standard. And then I'm introducing one more term here, FIRA. This is a consortium for wireless devices, specifically focusing on the UWB. So we run those compliance checks. And then we ship, we bundle the hardware and all the software layer stacks to the customer, right? And the customer gives us the feedback, customer is happy. And at that point, we sign off and say this SoC hardware plus software, the product is ready for rollout, and then we go to production, right? So this is the flow diagram I have listed for hardware front end, back end, and hardware software platform enablement. Let's move now into the UWB as a technology, right? So again, keep recollecting the basics of math and physics, right? So here in this line diagram, a simple line diagram, what we have is an initiator or a transmitter, if you will, and then we have a responder or a receiver, if you will, right? So the initiator or the transmitter, right? It transmits a RF signal, radio signal, right? Which we know propagates at the speed of light, which is 3 into 10 to the power 8 meters per second. So the transmitted ray, right? So it will arrive at the target or at the receiver through multiple paths. One is a direct path, right, through the medium, right? And then other signal could be reflected off the floor, if you will, here, then bounce off another object, on more reflection, and then the reflection ends on the target. Right. Another could be a single hop from the transmitter, one hop to the receiver. Now, each of these signals, they arrive at the receiver or at the target with different intensities, right? Based on the medium they are traveling through, whether they have been absorbed, reflected, refracted, or even diffraction, right? So this forms the basics of physics or optics of the wave propagation. Now let's go to the next file. Again, UWB technology. This is the graph here. The x-axis shows the frequency in which we operate, and the y-axis shows the spectral density, right? So if we take examples of the green band, right, narrow band wireless communication, right? So these operate in the narrow band with a bandwidth of 1 megahertz, right? And Bluetooth, for example. There are other wireless communications which operate at 20 megahertz bandwidth, Wi-Fi, for example, right? Whereas UWB, if you see the blue parabola or blob at the bottom, so UWB, it sends, receives very short pulses with very low power spectral intensity, right? Across a wide 500 megahertz spectrum, right? So the benefit why UWB operates here is this gives us very limited or no interference with existing Wi-Fi technologies, right? So this is the power spectrum of UWB. Now let's kind of start a bit deep dive into the UWB ranging techniques, right? Again, this file looks a bit busy, but the way I learned UWB is like you have to look at basics of physics, right? What we have here is an initiator, and we have a responder, and we need to calculate what's the time, right? Or what is the distance, for example. Right? Again, it's basic physics. So let's do it one at a time here. So in this ranging technique, it's called single-sided two-way ranging. We are trying to measure the time of flight it takes for the radio waves to travel from the transmitter or the initiator to the responder, which is the receiver, right? So here in this frame, if you follow my cursor, right? So the transmitter sends out a pole, right? And this distance taken from TXA to RXB, this is the time of flight between A to B. Then the receiver or the responder processes the pole which has come, and that's the reply time. And then through its transmitter, it sends back a response to the initiator, right? So that's the time of flight between B and A. That's the responder and the initiator, right? So now we need to calculate the time of flight, right? So how do we do that, right? So if you look at the equation here, the transmitter has sent a pole. What is the time taken for the pole as a response to come back to its receiver, right? That forms the loop, right? So that is a loop time. And this is the processing time by the receiver. So if you look at this equation, again, physics says time is equal to, right? Hey, it's distance and whatever the speed, right? So here we're just saying time. This is the loop time it is taken minus I remove the reply, and it's a two-way path. So I divide by 2, I get my time of flight, right? So this is one application of a single side two-way ranging, which UWB supports, right? Likewise, let's go now. Let's say again the same scenario here. It's called double-sided two-way ranging. So let's add one more variable here, right? Let's say again going back to the engineering of communication as a subject, right? So whenever we do communication, right, we have some concept called where we embed the clock as part of the data, so the receiver can perform a clock data recovery, right? So that way, the transmitter and receiver they kind of are in sync, or we know that they are synchronous or operate with an alignment, right, with a determinism. So now, let's say there is a clock difference between the transmitter and the receiver, right? There is a misalignment. Now, how do we get a reference, right? So what we do here is we do two single-side ranging. We call it double-sided two-way ranging, right? So we have the transmitter sending the pole. There is a processing time by the receiver. The receiver replies back with a pole plus response time. Then the transmitter sends a third frame or a third packet, and the receiver calculates its loop time, right? So we have two checks here. So this is what it is called as double-sided two-way ranging mechanism. Again, basic equation here, the time of flight. We have two loops that is on the initiator or transmitter, and one more loop on the responder, right? So we multiply both the loop times, then we subtract the reply time of the initiator, and then in the denominator we have all the delays, right? So this kind of gives us the double-sided two-way ranging time of flight. Okay, let's go now a new kind of ranging technique. Here, we're trying to calculate the time difference of arrival, right? So pay attention to the diagram on the bottom left. This is interesting, right? In the previous scenarios, we had a wireless device which was doing the ranging, single side two-way ranging or double side two-way ranging. Here, we have four anchors, A1, A2, A3, A4. The four anchors are routed. The distances between anchors is known, right? Whereas the wireless gadget is moving, right? So now here the ranging scenario is we need to locate, for example, an indoor location, or for example, on a factory floor. We need to locate where this wireless UWB enabled wireless device is, right? So the initiator sends a packet or a blink. All the four anchors receive it, right? Again, based on the distance from the initiator, each of these anchors receive the UWB pulse at different time intervals as shown by this timing diagram, right? So if we can calculate, we know the distance separation of all the four anchors and we know the time taken. So we have the distance, we have the time, right? So then we can calculate the time difference of arrival, right? So this is one more UWB solution, right? Now, one key point here is we need all the four anchors to have reference to be synchronized, right? So this induces additional hardware complexity and then software development to ensure that we do the ranging correctly, right? So this is one scenario. Then let's go to one more fourth scenario, or a fourth ranging technique, if you will, right? So here, bottom left, what we have is a wireless gadget, right? And it has on the back side two antennas. So let's zoom in. So we have two antennas here on the back of the wireless gadget, right? Now there is a point A, right? We would like to know the angle of arrival or the theta, right? So again, if you look at if you again recall the geometric properties of a circle, right? So this forms a sector, right? So we would want to know what is angle of arrival or the theta, right? So what we have here is one antenna, it's combined with the TX and RX1, right? So the TX sends out a request and we receive a response back, right? And this is received by two receivers, which are separated by distance D, right? This is known. So RX1 receives a response, RX2, it receives a response, right? Now we need to calculate, so if you can visualize, right, this forms the sector and we need to calculate this theta here, right? So we know the phase difference between these two, between the two receivers, right? That's RX1 and RX2. Phase difference is calculated as part of the carrier signal, right? And once we have the one variable we have is a phase difference. And then we look at the circumference circle, it's 2 pi r. So the way to break it down is 2 pi into the frequency and the delta t. The delta is the distance the two responses have been received, right? So how do we calculate again? Basic physics here, time is equal to distance by speed, right? So here delta d, we replace time with the distance and the speed of light c, right? So what we have, the equation we have derived here is 2 pi into the distance d, small d, between the two RX1 and RX2 receivers or the responders, and cos theta, right? Again, trigonometry, right? And frequency, we get to the denominator becomes 1 by f, that's the lambda, right? So now we transpose the right-hand side to the left-hand side to calculate theta or the angle of arrival. So that's a cos of the phase difference into lambda, and the denominator is 2 pi into d, or this is the sector length or the d distance. So this is a fourth ranging technique, right? And now let's move on to UWB frame, what does frame look like? What is the structure of the frame, right? So UWB frame, it's made of single pulses of different polarities, right? And the structure of the frame is broken down into there is a preamble in the beginning, right? And then there is a start of frame delimiter, right? And then there is a STS or a scrambled time sequence, if you will. This enables us, for example, we discussed user Theo was trying to unlock his car, right? And hacker can intercept a signal and gain access to the car, right? So what we do is we have a timer and then we kind of scramble with using the timer equation and a polynomial. We generate this STS or the scramble timestamp. We embed it as part of the UWB frame. And then we have a physical header. And then we have a payload or a PSDU, which could be a few bytes to kilobytes based on the usage use case and the usage scenario, right? So this forms the UWB frame, a preamble, SFD, STS, EHR, and a payload, right? And these pulses of different polarity, these are transmitted again, as shown here. These are very low pulses. We discussed the spectrum, right? So this supports ranging as well as the payload transmission, right? When say payload transmission, some messaging between the initiator and the responder, right? So this standard existed. UWB as a technology is a legacy or a classic technology, but it's now in the smart world. There is a technology and opportunity to deploy UWB, right? So STS, I've already explained the secure ranging, it enables secure ranging, and the frame optimization. There are mandatory and optional packets as part of this frame. Then based on the SNR, signal to noise ratio, we do the frame optimization. Right, let's go to the next file. So let's now apply our learning of math, physics, and UWB ranging techniques, right? So now as a hardware engineer, as a software engineer, right now we need to come up with a solution, right, for UWB. Right, hardware as well as software, and we discuss the methodology. So what all IPs or hardware components or software components we need to develop, right? So we discussed mathematical operations, right? To perform the mathematical operations, we require a processor, CPU system, right? That's one IP. And then we discussed initiator or transmitter, responder or receiver. So for the baseband signals, for performing the Fourier transforms within frequency domain to time domain, right? So we need a signal processing system or a DSP, digital signal processor. Then for the wireless transmission for RF signal, right, we need a front end, which means that within our hardware, we need a digital to analog converter, which goes out on the RF front end and then goes to the TX antenna. And we also need for the responder, when it sends a signal back for the initiator to receive the signal, it receives via the front end. And then we need to convert that analog pulse or the analog signal in terms of amplitude or frequency into digital, right? That's the ADC. Then we need a on-chip bus system to perform write-read operations to all these IP modules, CPU, digital signal processor, ADC, and the DAC, right? Then when we power on the hardware, we need memories, which kind of tell the hardware what is the boot up configuration it should power on, right? So those could be boot ROMs, those could be flash memories, right? And then these memories are also required when we do the math operations. We need to store the intermediate results or some of the variables which are related to the ranging distance or the angle of arrival, which come from the ranging packets, which keep going out, right? Yeah, we keep transmitting the ranging and we keep computing the distance and the angle, right? So now then for accuracy, right? The physics says time, distance, speed, right? Speed is constant, time and distance vary. To keep time to measure time for ranging sessions, right? So we need oscillator, we need parallel clocks for timers, for counters on the chip. And then we need voltage regulators to power up the entire chip hardware, right? So this forms the hardware IP portion of it, to speak in a generic sense. And then from the software side, we need the software boot code, which resides in the boot memory and then boots the chip. And then and then it goes fetches the instructions, and then we have the software firmware, which exercises all the UWB scenarios, UWB features through the firmware routines. And then we have the middleware of the software, and then going up the OSI stack, we have the application layer, right? So this is how a UWB technology, we discussed ranging techniques, and then how we derive or scope out the hardware and the required software, which gets integrated onto the motherboard or the platform. Okay, let me go to the next file. So hardware software co-verification for quality. So today NXP ships UWB chips. This other dimension is the brand name. So for UWB dimension chips, the hardware and software has been integrated, has been validated. The ranging use case scenarios, these also have been verified, validated. The protocol parameters have been qualified, as well as the IEEE and the FIRA compliance checks. These have passed, right? Today, UWB products, these are shipped ahead of schedule with quality. And as we discussed in the methodology, right, the goal is to delight the customer with a fully functional silicon, right? And the customer is delighted, happy, then it translates to getting this SoC hardware, software to production rollout. Then UWB as an ecosystem, the use cases are still evolving. Hence, once we do a tape out, once we have the SoC or the silicon, it's critical to ensure the hardware and software co-verification. It has covered all the corner case scenarios, right? This will ensure that we continue to scale up the platform to support new use cases for the customer, right? So that's a critical part here. Now, let me kind of go over some of the existing UWB use cases in the smart world. I have a few files from the NXP web. Let me press through them. So this is what I would call as UWB intersection in our smart world. So here we have the user Theo. This is secure hands-free access. The user Theo in his pocket is carrying a UWB enabled wireless key fob, right? So as the user Theo approaches the car senses through ranging, right, that this user has approached the car with the centimeter accuracy, and UWB does the time of flight calculations, right? And due to the STS in the UWB frame, these are resistant to a hacker trying to intercept the communication between the user and the car, right? So this is one scenario, secure hands-free access. The same thing can be applied to a main door or any other access control pathway. Now, another example of UWB intersecting in our lives is indoor navigation. Let's say you're in a large building, in a shopping mall, or you're outdoors, right, inside a structure. So you would want to know where you parked your car, right? How do you go to your car? Or you would want to know within the huge building or where your friend is, right? You would want to go say hello, right? And you're picking up, you're doing shopping and you're picking up a few items on the shopping cart, right? And you would want to know where your shopping item is, right? So UWB will kind of guide you or help you do the indoor navigation down to the centimeter accuracy. Likewise, here is, given the pandemic time, hands-free payment, nothing like this, right? Contactless payment. So UWB, when you carry the UWB enabled smartphone in your pocket, right? So this acts as a wallet, right? And then as you approach the payment counter, right? So there is exchange of messaging between your UWB wireless enabled device, smartphone, and the payment point of sale, if you will, right? And then also you can the shop the establishment can also kind of share advertisements or preferences based on your profile or your interest, right? So that's what is shown here, right? You're walking past a billboard or advertisement, then based on your profile, your interests, the advertisement can change, right? Okay, here is one more intersection, credential sharing. This is something I really like it, right? So here what we have is we have the one user who has parked the car, let's say a rental car, and goes into the co-working office space. And this user can delegate or give access to another user to drive the same rental car. Again, this is wirelessly without having to physically exchange a key, or in case you are somewhere else, right? You can always still remotely delegate or give access of the rental car to another fellow coworker, right? Okay, this is again coming back inside the house, right? Today in our homes, we have wireless speakers, wireless key fobs, wireless earbuds, right? Now, uh, where did we drop them, or where did we kind of throw away inside the house, right? So UWB enables or guides you to where each of these items are within your household, right? So in this uh, uh, frame, what we are seeing is a wireless speaker, right? So UWB senses it where it is located. Likewise, other entertainment systems and speakers within your house. So UWB pinpoints down to centimeter accuracy with help of your smartphone. Okay, now coming to the references, these are references from the NXP website, how UWB is enabling the Apple phone or Apple iPhone or the Apple Watch, that ecosystem. So you could please go and look at these links, right? And that will give you a perspective of how the UWB ecosystem is enabling decision making as well as precision location for the user, right? There is one more link here on the UWB secure ultra wideband. This UWB dimension is the NXP brand for UWB solutions, hardware, software. So I'm not playing the video here, but when you get a time, please go and follow these links and look at this video as well, which gives access to a user who's approaching a entrance mechanism, right? Then for the audience who are looking at boosting, enhancing your career, hardware career, software career, yeah, please do apply to NXP today. Here is the NXP careers link. UWB is a fantastic technology to hone your technical skills, hardware, as well as the full software stack development. So yeah, please do apply. Okay, I'll now open up the floor for Q&A. Hey, Priyanka, please go ahead. Are there any questions on the Teams meeting, or users can ask their questions?